Okay, so we will start the discussion session 7. So as of now, we have studied the basics of fuzzy set theory. Then we studied fuzzy arithmetic, and that was followed by fuzzy relations. And the last module, so to speak, of this course is fuzzy logic, which is which can be seen as an extension of the classical logic that we are all familiar with. So this discussion session is going to be about logic in general. So what I want to do in this session is to give a context, a historical context, as well as a motivation for for fuzzy logic and general multi-valued logic. And you will soon see what that term means. So we'll start. So it is useful to start with the etymology of the word logic, right? So this word logic comes from the Greek word logos, and there is no definite English translation of this word. Uh, it's translated to reason, uh, rule, discourse, uh, in certain contexts, language as well, right? So for us, logic is going to be the study of correct reasoning. And this is basically how Wikipedia defines logic. Now, what exactly reasoning mean? It's essentially the act of making inferences, right? That is the act of arriving at a conclusion based on one or more piece of information. So if I say something like it is cloudy today, so it's likely that it is going to rain. So what I did just now, I made a conclusion that it is likely that it is going to rain today on the basis of the information that it is cloudy, right? So I arrived at a conclusion, I drew a conclusion based on a premise, and the premise being that it is cloudy today. So this is what reasoning means. It's the act of making inferences, which is basically drawing conclusion based on a set of premises. And there's a term that is often used when we study logic, and that is argument. So argument is nothing but a set of premises together with a conclusion. So the point that I just made, the example that I just took, that it is cloudy today and therefore it is likely that it will rain today, that is an argument, right? So we had a premise that it is cloudy, and then we had a conclusion that it is likely that it is going to rain today. So useful terminology to remember. And the primary objective of logic is to uh, figure out what are the correct ways of making inferences. Or in other words, if I say something like my name is Amrit, and that is and therefore Earth is round. Now I made an argument, right? And in this argument, the premise was my name is Amrit, and the conclusion was the Earth is round. Now, in isolation, the two statements, my name is Amrit and Earth is round, are correct. But does the conclusion, Earth is round, follow from the premise that my name is Amrit, right? So I would expect that many of you would say that it does not make sense. Uh, and therefore, it is reasonable to say that that is not a correct way of making inference. So in logic, we are primarily concerned with what are the ways of making correct inferences or correct arguments. Now, this study of logic is broadly categorized into two types. So we have something called as formal logic, and then we have informal logic. So in formal logic, we are primarily concerned about the structure of the argument. So if I say something if P then Q and P, and from here I infer Q, then it does not really matter what P and Q are. They could be anything. They could be any proposition, any statement. What we did in this particular example is we just focused on the structure of the argument, on the form of the argument, and not necessarily the content that P and Q carries. So that is what formal logic is about. It's about abstract form of the argument, and is that argument valid? And in general, in formal logic, we deal with arguments that are expressed in some kind of formal language. So this term formal language has a technical meaning. I don't want to go into that, but if you are someone who has taken a course in theory of computation, for example, then you would be aware that this term is is a technical term. But in the context of this session, just think it of as just a language, an artificial language, like a programming language, if you will, right? So the thing that you should remember is that in formal logic, we are concerned about the abstract form of the argument. We are concerned about structure and not necessarily the content. An example of a formal logic is mathematical logic. So it's if you have taken a course in mathematical logic, then you must have remembered that there we do not really talk about what P and Q stands for, right? We are only concerned about how P would imply Q and how Q would then imply some other proposition R and so on. Now, informal logic uh, has to do with arguments that are expressed in natural language. So the language that I'm speaking right now is English. English is a natural language, Sanskrit is a natural language, Tamil is a natural language, and so on. So these are languages that we human beings speak, right? These are languages that have evolved with time, um, right? And informal logic is about examining arguments expressed in those natural languages. And the focus of informal logic, unlike formal logic, is about content, right? So if I say something P if Q, then in formal logic, we would ask questions as to what P and Q mean, right? Are they factually accurate or do they have any practical relevance, right? So that is the main distinction between formal and informal logic. Formal logic is about the abstract structure or form of the argument, and informal logic has to do more with the content of the argument, the proposition involved in the argument. And the reasoning that we do in everyday communication is an example of the study of reasoning in everyday communication would fall under informal logic, right? Because in everyday language, we just do not make inferences like a robot, right? Our inferences are based on the meaning of the sentences that we are uttering. So that's an example of informal logic. Now, uh, there have been many logical traditions around the world. Uh, One is, of course, the Aristotelian logic, but it is useful to know that there are many other kinds of logic as well. So you have Stoic logic, and if you come to India, you have Nyaya school of logic, and you have Chatuskoti, Saptabhangi, and so on. Now, Aristotelian logic is important in the sense that it is the main system of logic, at least in the Western world, and it formed the basis of mathematics for the longest time. And Aristotelian logic is based on this principle of bivalence. And this principle of bivalence essentially states that if you take any proposition, so maybe I should mention what the term proposition means, because it's a term that we will use quite often. So proposition is basically a declarative statement. So it's a statement that asserts something about the state of affairs in the world. For example, if I say, my name is Amrit, now that's a declarative statement. I'm declaring a fact about the world. New Delhi is capital of India. Again, a declarative statement, a statement that is asserting something about the world. Uh, a, a statement like, is uh, Bangalore located in Tamil Nadu? Now, that's not a declarative statement, right? Because it asks a question instead of declaring something about the world. So, such statements are not propositions. Propositions are statements that are declarative in nature, that declare something. Anyways, so what principle of bivalence says is that every proposition is either exactly true or exactly false. Uh, in other words, Aristotelian logic is 0, comma 1 valued. 0 standing for truth value false and 1 standing for truth value true, right? And I should mention a caveat here because if you look at the sentence, the word largely is in parentheses. So Aristotle, who gave Aristotelian logic, uh, was aware of the idea that certain propositions cannot be given a truth value that is exactly true or exactly false. So he was aware of that idea. And he, in fact, gave an example, the following example, that there will be a sea battle tomorrow. Now, consider this proposition. Now, what Aristotle argued that if we believe in the principle of bivalence, then this proposition is either going to be true or it is going to be false. But this determination of truth value cannot be done unless the day has passed and we have entered tomorrow, so to speak, right? So the future events, statements about future events, or what he called as future contingencies, propositions about future contingencies cannot be given a particular truth value, right? So the point is that Aristotle was aware that this business of assigning a truth value of 0, truth value of 1 to propositions is not always going to work. But he never really articulated this idea in great detail, right? So that's why it is safe to say that, largely speaking, Aristotelian logic is based on the principle of bivalence, or in other words, any proposition has truth value 0 or truth value 1. Now, eventually, with time, this Aristotelian logic was replaced with modern formal logic, starting in 18th century, in fact, 19th century, I should say, with the work of George Boole and Peirce and Frege, eventually leading to the theories of propositional logic and first order logic. Now, we will soon see what these two terms mean, but the point that you should remember is that with time, Aristotelian logic was replaced with more sophisticated theories of logic. However, this principle of bivalence, this idea that a proposition has truth value 0, truth value 1, remained. And systems of logic that are based on this principle of bivalence, this principle that a proposition has truth value 0 or truth value 1, are referred to as classical logics. Okay. So to summarize, there exist many traditions of logic. Aristotelian logic was particularly important because it formed the basis of mathematics, at least in the earlier times. And Aristotelian logic is based on this principle of bivalence, which is that a proposition has truth value 0 or truth value 1. Eventually, Aristotelian logic was replaced with more refined versions of logic, but this principle of bivalence, in a sense, remained unchallenged. Now, two particularly important systems of logic, classical logic, I should say, are propositional logic (PL) and first order logic (FOL). And they're extremely important in the sense that all of mathematics, almost all of mathematics, can be handled using PL and FOL. So, okay, so if you are not able to follow all the things that I'm saying right now, for example, I use the word handled. What exactly it means may not be very clear. So it is okay if you're not able to uh, understand completely all the statements that I'm making. But what you should attempt to do is get a sense of what uh, uh, get a broad sense of what I'm saying, right? Because this is not a course on mathematical logic, right? It's a course on fuzzy arithmetic, fuzzy sets, and so on. So I don't want to be very technical here. I can make all the statements that I've made so far very precise, but that's not the objective of this course. So you should focus on getting a sense instead of like being super concerned with understanding everything. So almost all of mathematics can be handled using PL and FOL. In other, basically mathematics that we have done so far, continuity, differentiability, topology, and so on, they all can be formulated in the language of propositional and first order logic. And therefore, the point is that it is useful to spend time understanding what these logics are. So I'll start with propositional logic. Now, again, uh, how do I put this? So I will describe what propositional logic is and first order logic is, but I will not be super precise, right? I won't be very technical. Rather, I would focus on covering the important aspects. So if you refer to a book on mathematical logic, you'll find that I'm saying things that are a bit sloppy, but that is okay, right? Because the objective of this course is very different. So I should start with the caveat that the exposition is a bit imprecise. Okay, so what is propositional logic? So in propositional logic, we start with a set of atomic propositions, or they're also called as formulas, generally denoted by lowercase letters, A1, A2, A3, and so on. And then we have a set of connectives. So we have this connective that for now on, I'm going to pronounce at wedge. This is V, this is neg, this is imply, and this is by imply. Okay, so I'm not reading these symbols as and or as of now, because the moment you read this symbol as and, there is automatically a meaning that comes up in your head. So when you, if I write something like P and Q, you automatically read it as P and Q. But before doing that, I just want to define the language of PL, right? So as of now, we are not concerned about meaning. We are not concerned about what this P symbol, whatever the symbol mean, Q mean, right? As of now, we are just interested about the language. What are these symbols are, right? So that's why I'm going to pronounce them as wedge, V, neg, imply, and by imply. So in propositional logic, we have a set of atoms, atomic propositions or formulas, whatever you want to call them, and we have a set of connectives. So we start with these five connectives, and using this connective, we can form more complex propositions. So more specifically, if you give me two propositions P and Q, or two formulas P and Q, whatever term you want to use, then I can form five new propositions like this. So P wedge Q, P V Q, neg P, P imply Q, and P by imply Q, right? So given two propositions P and Q and the connectives, these connectives, I can form five new propositions. And these propositions are valid propositions. So these are proper formulas. And secondly, only the propositions of the above form are valid. In other words, if I write something like, so this is not a valid proposition, because for a proposition to be valid, or a formula to be valid, it has to be either an atomic proposition or it has to be one of these five forms. And certainly, this sequence of symbols that I have wrote do not fall into any of these five types. So this is not a valid proposition. right? So to summarize, in propositional logic, we start with a set of atomic propositions or formulas and a set of connectives. Using these connectives, we can form more complex propositions. And only propositions of these 5 types are valid. Now, again, given these 5 propositions, we can make even more complicated propositions. So something like P and Q are union, something like this. But the point is that this is a valid proposition because if we let P dash to be P wedge Q and R dash to be R by implied T, then this statement, this proposition reduces to PR imply P prime imply R prime, right? And this is of the form fourth form, right? And therefore it's a valid proposition. So moving on. Now, any proposition has truth value 0 or truth value 1, right? We're talking about classical propositional logic, and therefore we'll have principle of bivalence here. So proposition is either going to be true, either going to be false, that is, its truth value is going to be 0, or it is going to be true. In other words, its truth value is going to be 1. Now, if truth values of proposition P and Q are known, then we can figure out the truth value of complex propositions P wedge Q, P VQ, neg P, P imply Q, and P by imply Q. So given truth values of P and Q, we can figure out truth value of this complex propositions. And the question is how? And this is how we determine the truth values of complex propositions. So, so if given a proposition P, I am denoting the truth value of P as this. So T of P. Although in many books and even resources on internet, you'll find that this T is not really used, right? But uh, you should appreciate the nuance that P, or for that matter, P wedge Q, or P VQ, or P imply Q, these are nothing but sequence of symbols, right? These are just symbols. So if you think of yourself as not a human being, but as a machine, a compiler, for example, then these sequence of symbols do not mean anything. They're just sequence of symbols that we are considering to be well formed. So we don't have assigned meaning to these sequence of symbols, right? And when we write T of P, we are actually assigning meaning to it. Meaning in the sense that we're assigning a truth value to it. So there's a distinction between P and T of P. P is just a symbol for us. You know, the symbol does not mean anything. It's just a symbol. But T of P is a truth value of P. So in other words, T of P is a meaning of the proposition P, right? So that's why using this symbol T of P is actually very instructive, right? Uh, because a proposition is different from its truth value. The proposition is just a symbol as of now. Okay, so moving on. So if truth value of P is 1, truth value of neg P is 0. And if truth value of 0, if truth value of P is 0, then truth value of neg P is 1. Similarly, if truth value of P and Q are both 0, then truth value of P wedge Q is 0. And similarly, you have these conditions for other truth values of P and Q. This is how P V Q is defined, and this is how truth value of P imply Q is defined, and this is how the truth value of P by imply Q is defined. Now it is easy to see that truth value of P and Q is nothing but minimum of truth value of P and truth value of Q. Similarly, truth value of P VQ is nothing but maximum of truth value of P and truth value of Q. Similarly, in this case, truth value of neg p is nothing but 1 minus truth value. All right. So I hope that's pretty obvious. Now, what about truth value of p imply q? Can we express it as some function of truth value of p and truth value of q? Now, you can try doing that on your own, and you can try coming up with different formulas. One formula that seems to work is this, right? So let us verify if this formula actually works. If so, maybe I'll just write it here. So in this case, we have 0, comma 0, so it's 1. In this case, you have, it's again 1. In this case, you have, so this formula indeed works, right? You can observe that this formula works as well. The minimum of 1 comma 1 minus tp plus tq. In fact, you can also see that this formula works as well. Okay. So there are a variety of formula that seem to work for the truth value of p imply q. In fact, in this particular case, truth value of p wedge q, instead of taking minimum of tp and tq, you could have taken tp dot tq, right? So the point is that the truth value of the complex proposition made out of p and q can be expressed as some functions of truth values of p and q, the individual truth values of p and q. Okay. And then we again have this by truth value by imply p and p by imply q. And if you look at this truth table closely, it turns out that p by imply q is true if and only if the truth value of p and truth value q are same. So when both of them are 0, we get truth value of 1. And when both of them are 1, we get a 1. And in all other cases, we have 0. So p by imply q is true if and only if truth value of p is same as truth value of q. So that's an observation that can be made from this table. So long story short, given propositions p and q, we can make complex propositions using the set of 5 connectives. And given the truth value of the propositions p and q, we can also determine the truth value of these complex propositions. And how do we do that is basically given by these truth tables. Now that we have seen how the truth values of p wedge q, p vq, and so on, maybe I'll write them again. Now that we have seen how the truth value, how do these connectives, wedge, v, neg, imply, and by imply behave in relation to the truth values, we can assign following interpretation for the symbols. So this neg, the symbol that we have been reading as neg so far, can be called negation. Because if you look at this truth table, it says that this neg p, this symbol neg p, is going to be true if and only if p is going to be false, right? So if p is true, then this neg p is false. And if p is false, then this neg p is true. So this is how negation behave in natural language, right? We say that today is Tuesday. If it is today's how do okay, so maybe I should think of a better example. So if I say that f of x equals to x squared plus x plus 1 is a linear function, then we know that this statement is false. So therefore, its negation, f of x is not a linear function, is going to be true. So that's how the word not behaves in English, in natural language. And if you look at the truth table of this neg p, we see that the truth value of neg p corresponds to how the word not is used in the natural language. And therefore, this symbol that we have been calling neg so far can simply be read as negation because it behaves exactly as not, the word not in English language. Similarly, if you look at this symbol that we have been calling wedge so far, it behaves exactly like and or conjunction in natural language. So we say that I live in Delhi and Delhi is located in India. This statement will be true only when the individual statements I live in Delhi and Delhi is located in India are going to be true, right? That's how the word and behaves in the English language. And if you look at how the truth value of this P wedge Q is defined, it turns out that this is how exactly the word and behaves in natural language. So the point is that this wedge can be read as and, okay? And similarly, the symbol V can be read as or, and the symbol that we have been calling as imply can be read as implied, right? So the point is that we started with a set of symbols, A1, A2, A3, A4, so on, and we call them atomic propositions. And then then we had another set of symbols, neg, wedge, v, imply, and so on. But you got to realize that those are just symbols. We did not give them any meaning. And then we said that using these atomic propositions and these symbols, these connectives, we can form more complex propositions. And then we define how do we do that. And having made those complex propositions from atomic propositions and connectives, we then argued that the truth values or the meaning of these complex propositions can be derived from the meaning, or in other words, truth values of P and Q, right? And this is how the truth values of those complex propositions are derived using the meaning of P and Q, that is, truth values of P and Q. And then we paid attention to the fact that these connectives, these symbols neg, wedge, and v, behave in exactly the similar manner as the word not, and or in English language. And therefore, it makes sense them to simply call them negation and or imply and if and only if, right? So you have to understand this nuance that the symbols come first and then we define their truth values. And it turns out that the truth values corresponds to certain words in the natural language. And therefore, that is the reason why I pronounce them in a certain way. Anyways, so we now have a sense of what propositional logic PL is about. We have atomic propositions, we have connectives, from there we form complex propositions, and the truth values of these complex propositions can be derived from atomic from the truth values of atomic propositions. So this is what we have done so far. Now there are certain concepts in propositional logic, and one such concept is the concept of logical equivalence. So if I give you two formulas, two propositions, whatever you want to call them, P and Q, then we call them logically equivalent, which is denoted by this symbol, if P and Q assume the same truth value for all the truth value assignments. So regardless of what the atomic propositions, what are the truth values of atomic propositions are, P and Q are always going to have the same truth value. In that case, we call P and Q to be logically equivalent. So if we have to think this concept of logical equivalence in terms of truth tables, then P and Q are logically equivalent if P and Q have precisely the same truth tables, right? So in other words, so, so these four are examples of logically equivalent formulas. So P and Q, P imply Q is a formula, not P or Q is again a formula. Now, as sequence of symbols, they are different, right? Because this particular formula, the first formula starts with proposition P, the symbol for P, and then we have another symbol imply, and then we have another symbol Q. And the second formula is different from the first formula syntactically, right? So the second formula starts with this symbol not, and then we have P, and then we have brackets, and then we have or, and then we have Q. So these are syntactically different. That is, as sequence of symbols, they are different, but meaning-wise, they are same. In other words, their truth values are always going to be same, regardless of what are the truth value assignments of atomic propositions. Okay, or in other words, P and Q are going to have the same truth values. So these are four examples of logically equivalent formulas. So let us see if that is actually the case. So let us try to determine if this formula P imply Q. So let us call this F1 and let us call this F2. Let us determine if F1 is actually logically equivalent to F2 or not. So we will draw the truth tables of F1 and F2. Okay. So we'll have 5 columns, right? So we have first column for P, we have second column for Q, and then we have third column for P imply Q, which is basically nothing but F1. And then we have the last column for F2, which is not P or Q. Now notice that I should have written T of P, T of Q, T of P imply Q, T of not P, T of not Q, right? Because we are now talking about truth values, right? And just a while back, I made this entire remark about how P imply Q is just a sequence of symbol. It does not mean anything. But T of P imply Q means something. It is basically the truth value. But this is a useful distinction to know. But in practice, we often drop this T when drawing the truth table, right? So I will simply write P, Q, P imply Q, and so on. But you should remember that these are actually truth values, right? But writing T of P repeatedly is cumbersome, so we simply drop the P, right? But always remember that we're talking about truth values. We're talking about meaning of propositions when we draw truth tables. Anyways, so P and Q. Now this P and Q, we can have 4 combination of truth values for P and Q, and we know from the truth table of P imply Q that P imply Q is true in all the cases except when P is true and Q is false, that we have seen. So therefore, we get the truth table for the first formula, formula F1, which is basically P imply Q. Now let us calculate the truth value of F2, which is not P or Q. So not P or Q. So first of all, let us draw the truth table for not P. So again, remember not P is true when P is false, and not P is false when P is true. So when P is truth value of P is 0, truth value of not P will be 1. Similarly, we'll have a 1 here, and then we'll have 0 zeros. And then we need to draw. Then we will now draw the truth table of not P or Q. Right. So this is basically the truth table of not P, and this is the truth table of not Q. Right. Now let us apply or this particular symbol between them. Now we know that P or Q is true in all the cases except when both of them are false. Right. To confirm, we go back to the truth table of how the symbol V, and we see that P is false. That is, the truth value of P or Q is 0 only when truth value of P and truth value of Q are both 0. In all the other cases, it is 1, right? So we use that information. So we focus on the truth value of not P and truth value of Q, and then we draw the truth value of F2, which is not P or Q. So this will be 0 and 1. When we take the conjunction, we get a 1. This is again 1. This is 0. And this is again 1. And we notice that the truth value of F2, truth table of F2 is same as the truth table of F1. So 1 is equals to 1. 1 is again equals to 1. 0 is equals to 0 and 1 is equals to 1. So in other words, this thing, this proposition is logically equivalent to this proposition. Okay. Let us do the next example. So we have not of, okay, so maybe I should use, so we have been using, so just a remark, the symbol neg is also denoted by this particular symbol, right? So you have all like a half T. So in some books you'll find they have used the symbol tilde or what we have called neg, and in some books you'll find this half T, right? So they are used interchangeably, and which is what I'm doing in these slides as well. So don't get confused. What is this new symbol half T? It's just negation, neg. Okay. So we have another example, and let us see if these two propositions are actually logically equivalent. This is F1 and this is F2. So we start by drawing the columns for P and Q. Then we know that the truth table of P and Q is like this. It's true only when both P and Q are true. And then if we take the negation, we'll get 1, 1, 1, 0, right? Because negation of a proposition is true if and only if that proposition is false. Okay. Now we will draw the truth table of not P. So this will be 1, 1, 0, 0, right? Because we have 0, 0 and 1, 1. And similarly, now we'll draw the truth table for not Q. So this will be 1, 0, 1, 0, right? So I'm just looking at Q and I'm drawing the truth table of not Q. And then we'll draw the truth table of not P or Q, that is F2. So we essentially have to apply the OR connective on these two truth tables. So let us do that. So 1, 1, 1, 0, right? And then we notice that the truth table of F1 and truth table of F2 are same. In other words, F1 is logically equivalent to F2, or in other words, not of P and Q is equivalent to not P or not Q. So I hope that you are familiar with an identity like this. In set theory, we have something like this, right? Intersection of complement of intersection of A and B is union of complements of A and B. And this look something similar. Instead of intersection, we have an and. Instead of complement, we have or negation. And instead of union, we have or, right? And this used to be called De Morgan's law. This is in fact called De Morgan's law in context of set theory. And in logic also, we call this De Morgan's law. Okay. Similarly, I would encourage you to verify that these two propositions are logically equivalent. So how are you going to do that? Draw the truth table, list out the possible truth value assignments for P and Q. So the first two columns do that. Then draw the table, then draw the truth tables step by step. So we want the truth table of not of P or Q. So first draw the truth table of P or Q, and then step by step draw the truth table of not P or Q. And now we want the truth table of this expression F2. So first draw the truth table of not P, then draw the truth table of not Q, and then finally draw the truth table of entire F2. Right? So take this as a homework. And similarly, you can verify that P by imply Q is logically equivalent to P imply Q and Q imply P. So maybe I'll do this quickly. So we have the truth values for P and Q listed in the first two columns. And we know that this is how the P by imply Qs is defined. This is how the truth table of P by imply Q is defined, right? This is what we did in the second slide on propositional logic. Now so this is basically the truth table of the first proposition. Now we want the truth table of this proposition on the right hand side. So we will now draw the truth table of that proposition. So if we first draw the truth table of P imply Q, then we draw the truth table of Q imply P, and then we finally draw the truth table of entire F. So what will be P imply Q? We know that P imply Q is true in all the cases except when P is true and Q is false. So this is 1, 1, 0, 1. Similarly, Q imply P is going to be true in all the cases except when Q is true and P is false. So this is 1, this is 0, this is 1, and this is 1. Now let us take the AND. So this is 0, 0. And we notice the truth table of P by imply Q is equivalent to truth table of P imply Q and Q imply P. So what this suggests, this logical equivalence suggests, is that we don't really need, in a sense, we don't really need this new connective. We can derive this new connective in terms of imply and AND. These two connectives are enough to obtain this connective by imply. And this is actually a very interesting point because in mathematics, we don't want to start with a lot of things, right? We want to have as little connectives as possible. And we want to be able to then do a lot of logic, right? So just a minute. So we have these 5 connectives, right? Not, or, not, and, or, imply, and by imply. Now this first logical equivalence suggests that you don't even need imply because it can be expressed as in terms of negation and or. So in a sense, we don't really need this. And we already saw that this by imply can be expressed in terms of not and this imply and this and. And we know that this imply in turns can be written in terms of not and or. So we don't even need this, right? These 3 connectives are enough. Not and or are enough to describe imply and by imply. Now, interestingly, you don't even need both and or. Or can be defined in terms of and. So I encourage you to see that P or Q is logically equivalent of not. This is nothing but De Morgan's law actually. So it turns out that you don't even need or. All you need is just not and you're good to go. You can describe both or imply and by imply in terms of these two connectives. And if if you're not happy with and, you could actually take or instead. In which case you'll define and like this. So the point is that we may get a sense that we have a big set of connectives, but under the hood, you only have a very small set of connectives because in terms of those small set, you can describe all the other connectives. So the term that is used is that these are complete set of connectives. Complete why? Because other connectives can be derived in terms of these two. Anyways, so this basically concludes uh, the concept of logical equivalence. Now, this implication, this P imply Q is pretty interesting because if you think about theorems in mathematics, they are essentially statements of the form, they are propositions of the form P imply Q. So if F is differentiable, then F is continuous, right? If A is a square matrix, then blah, 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 right? So all theorems in mathematics are nothing but P imply Q statements, right? So it is worthwhile to pay special attention to these, right? So given formulas P and Q, P imply Q is a formula, that much we know. Now we read it as P implies Q. Another way to read it as Q if P, and another way is P only if Q, right? So these are just different ways of reading this formula. P, this symbol, and Q. Okay. Now we say that P logically implies Q, or equivalently, Q is logically implied by P if this proposition P imply Q is a okay. So I have not defined tautology as of now, have I? No. So maybe okay. So I'll come back to that those slides, but before that, I'll define two concepts: tautology and contradiction. Once we are done with these two concepts, we'll move back to that slide. Okay, so given a proposition or a formula P, we call it a tautology if it is true for all the truth value assignments, right? So regardless of what the atomic propositions truth values are, P is always going to be true. Or in other words, the truth value of truth table of P consists of all ones. You won't find a zero there. It's all ones. So for instance, let us consider this formula. So you have P imply Q, and then it again implies P, and then you have this big complicated formula. And let us try to evaluate its truth table. So we begin by listing the possible truth values of P and Q, and then we draw the truth table of P imply Q. So this is 1, 1, 0, 1. So I hope by now you remember the truth table of P imply Q, right? It's 1 in all the cases except when P is true and Q is false. That is in this particular case. Okay. Now we know the truth table of P imply Q. So let us now compute the truth value, a truth table of P imply Q. This whole thing imply P. Again, it's going to be 1 in all the cases except this thing is false and this thing is true. That is, in the first case, it is going to be 0. In the second case, it's going to be 0. In the third case, it's going to be 1, and this is going to be 1. Okay. And then we'll finally evaluate the truth table of this entire formula. So we'll focus on the truth value of this thing, truth table of this thing, and the truth table of P. So 0 implies 0, it's 1, 1, 1, and 1. Right? So the truth table of this formula, let us call this formula F, has all ones, which means that regardless of the truth value assignments of P and Q, F is always going to be true. And therefore, it's called tautology. So tautology is nothing but a proposition, a formula that is true all the times. In other words, its truth table is just all ones. So I hope you got this sense. In fact, this particular tautology has a name. It's called Peirce law, if I'm not mistaken. Anyways, similar to tautology, we have a concept of contradiction. So tautology is a formula or a proposition that is true all the times, a contradiction is a formula that is false all the time. So that is a formula P is called a contradiction if it is false for all the truth value assignments. In other words, its truth table consists of all zeros. So this is an example of a contradiction. P implies Q, this whole thing, and P and not Q. Now let us verify if this is actually a contradiction. So we list the truth values for P and Q, and then we draw the truth table for P imply Q. So I hope you remember this is 1, 1, 0, 1. Then we compute the truth table of not Q. This is 1, 0, 1, 0. And now we compute the truth value of P and not Q. So this is 0, 0, 0. Sorry, so this is 1, right? So we are focusing on P and we are focusing on not Q. So P, A and B is going to be true only when both A and B are true, right? So that's how I'm computing the truth table of P and not Q. So 0, 0, 1, 0. Now let us now finally compute the truth table of this formula. Let us call this F. So we have to focus on this and this. So this is 0, this is 0, this is 0, and this is again 0. In other words, the truth value F, the truth value of F is always 0, regardless of the truth values of P and Q. In other words, F is a contradiction. Okay. So we have tautology, a formula that is always true, and then we have a contradiction, a formula that is always false. Now, let's go back to the slide. Right. So as I said, that P implies Q is it's an interesting formula because all theorems in mathematics are essentially of the form P imply Q. And we saw that P imply Q is read as P implies Q, and then Q if P or P only if Q. Or sometimes it's also said that P is a sufficient condition for Q. Q is a necessary condition for P. So these are just different ways of stating that P implies Q. And we say that P logically implies Q, or another way of saying the same thing is that Q is logically implied by P if this formula P implies Q is a tautology. So if we are able to establish that P implies Q is always true, regardless of the truth values of atomic propositions, then we say that P logically implies Q, or in other words, Q is logically implied by P. So let us see if, let us see if logically implies or in other words, if is logically implied to check this, we look at the proposition, we look at this proposition. So this implies this. And we'll check if this is a tautology. Okay, so let us do that. So here we have three propositions, atomic propositions P, Q, and R. And therefore, we are going to have a big truth table because P, Q, and R individually can have two truth values. So taken together, they'll have 2 cube, that is 8 truth values. So we'll just store 8 truth values in the first three columns. And then we will move towards computing the truth table of this complicated formula. Let us call it F. So let us first compute the truth of the first component, P or Q. So this is 0, 0. Okay. Sorry. Yeah, this is true. This is one, 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 this is one. And now let us evaluate this. Right? And finally, we have this. In other words, so I am not going to go through as to how these truth tables are computed. I hope that is clear by now, right? We are just using the truth tables of or, negation, and imply, and using that we are, you know, mo- computing the truth table of f step by step. So we first compute the truth value of this p or q, then we compute the truth table of not p or r, and then we finally take their negation to compute this truth table of this bigger expression, and then finally we compute the truth table for the entire formula f. The point is that f always has the truth value 1 regardless of truth values of p, q, and r. In other words, f is a tautology. Therefore, it is indeed the case that this logically implies this, which is Q or R. Or in other words, Q or R is logically implied by this big expression. Okay, now moving on. So all this discussion, all this training that we have acquired regarding propositional logic actually help us understand natural language better, right? Because often in English or the language in our native language, we make complicated statements, right? And one can better understand such complicated statements by breaking them into simple propositions and analyzing those simple propositions individually, right? So, to take an example, let us consider this fairly long statement in English. In order to get a driver's license, a person must pass the written test and also pass either the road test or the advanced simulation test. But that's a mouthful, right? We have a big natural language statement, we have a big English statement. Now, what this statement says is the following. So, this part, in order to get a driver's license, we captured this using the proposition P. That is, P has driving license. So P, the proposition P stands for person has driving license. And this huge statement we capture using proposition Q. So Q stands for person must pass the written test and also pass either the road test or the advanced simulation test. So we are setting that big statement to be Q and the statement that person has driving license as P. So this natural language statement essentially conveys this, that P logically implies Q. In other words, if P has a driving license, then it must be the case that P has passed the written test or also and also has passed either the road test or the advanced simulation test, right? So I hope you're able to see that this is nothing but this. So try to convince yourself that this is indeed the case. A common mistake to commit here is that you'll say that this actually means Q implies P because we have this term in order, right? So that can create a bit of confusion. So it is tempting to say that this a person passing the written test or and the road test or the advanced simulation test is a sufficient condition for him to get a license. But that is not what it means, right? Because what if we have a 10-year-old kid who has passed the written test and this road test and advanced simulation test? that person won't be eligible for the driving license, right? So the fact that someone has driving license implies that that particular person has passed the written test and passed the road test or the advanced simulation test. So what we have here is not Q implies P, but we have P logically implies Q. Okay. So I hope that is meaningful for you. Now, it is clear that this expression Q, this proposition Q itself can be seen as being composed of smaller statements. So we can decompose Q like this: R1 and R2 or R3, where R1 is person must pass the written test, R2 is person must pass the road test, and R3 is person must pass the advanced simulation test. So this part, either the road test or the advanced simulation test, it can be logically modeled as R2 or R3. And this whole thing, person must pass the written test and this thing can be captured as R1 and R2 or R3. So in other words, this big statement that we started with can be translated to P logically implies R1 and R2 or R3, where propositions P and Ri's are stated like this. Okay. Now, suppose I want to take the negation of this statement. We have a statement in English language and I want to negate it. So what do I mean by that? Suppose I say that f is some function from R to R, and we say that f is differentiable, logically implies f is continuous. We know that this statement is actually true, right? Because every differentiable function from R to R is actually a continuous function. But suppose I have this statement, I want to negate it. Then how do we do that? We essentially produce a counter example, right? That is, we find a function f that is differentiable, but f is not continuous. Whenever we have a statement like P imply Q, and we know that P imply Q is true, in other words, P logically implies Q, then in order to negate that, we find a situation where P is true but Q is false, right? So that helps us establish the negation of the statement P logically implies Q, right? So in other words, if I want to negate the statement, what do I do then? So we'll have to basically we'll have to consider the case when the person has a driving license that is P holds, or in other words, F is differentiable. So if it helps, think it of as P and think of this as not Q, right? So this is P and this is Q. So if we want to negate P logically implies Q, we that is essentially is P but not Q. So if I want to negate this huge expression, then we have P but not Q. But we'll just use De Morgan's law. In other words, person P has a driving license, but person has driving license, but not R1. That is, person has not passed the written test. So maybe I'll write this. Person has driving license. So this corresponds to the P part. Then not R1. So person has not passed the written test and sorry, so there was a mistake here, right? I'm applying the De Morgan's law. So this will become not R1 and this and will become OR, right? So I hope that was clear. So person has not passed the written test, which is not R1, or the person, so we have not R2. So the person has not passed the road test and not R3. So and the person has not passed the advanced simulation test. So I'll just abbreviate it as AST. So negation of this statement is the person has driving license, but person has not passed the written test, or the person has not passed the road test and the advanced simulation test. Right now, if I translate it into a grammatically correct natural language statement, it basically this. So it is possible for a person to get a driver's license even though they have failed the written test, not R1, or is this, and they have failed both the road test and the advanced simulation test. And this is basically key. So the point is that having a training in propositional logic allows us to better analyze statements in natural languages, right? So it, in a sense, makes you a better thinker, a better argumentator, because then you can look at a statement, you can identify its logical structure, and that identification helps you argue better. For example, how do I negate this big expression? How do I negate this big statement? Right? What are the important what is the P, what is the Q here? What is P imply Q here? Right? So learning propositional logic in a sense is actually really beneficial. Now, so this concludes basically the part on propositional logic. Now I will go to first order logic, which is often abbreviated as FOL, FOL. Now, in propositional logic, we had atomic propositions, and then we had connectives. So in a sense, the syntax of PL, propositional logic, can involve atomic propositions and connectives. And using these two things, we are able to form complex propositions. And first order logic, in addition to propositions and connectives, we have predicates and then we have quantifiers, which we denote using these symbols. And these quantifiers help us quantify predicates. Now, what exactly is a predicate? So this is something that I discussed in the last session as well, right? So I don't want to belabor the point. I'll quickly go through the definitions and then we'll move towards multi-valued logic. So a predicate is a function of one or more variables that yields a proposition for any assignment of value variables. So suppose I have a function phi, and this function phi is a function of one variable x. Okay. And suppose x is located in Tamil Nadu. Now this is a predicate. So predicate is basically a function of one or more variables. In this case, it's a variable of x, and it basically expresses some property, some declarative statement, some fact about the world, right? So in this case, predicate phi, which is a function of x, stands for x is located in Tamil Nadu. Now, the moment I substitute a particular value for x, so maybe Chennai, I get a proposition. So remember, a proposition is a declarative statement. It asserts a fact about the world. And the moment you substitute a particular value in a predicate, you obtain a proposition, you obtain a declarative statement. So when you substitute Chennai in X, you get Chennai is located in Tamil Nadu. Similarly, if you substitute Ooty in place of X, you'll get Ooty is located in Tamil Nadu and so on. So a predicate is function of one or more variables. So in this case, we just had one variable X, but it can be two variables, right? So we can have something like X is the supervisor of Y. So the moment you substitute specific values for X and Y, you'll get a declarative statement, you'll get a proposition. And this could be, and of course, by all means can be mathematical. So maybe X is less than equals to sine of Y, right? So the thing to remember is that a predicate is a function of one or more variables. And the moment you substitute specific value for those variables, you end up getting a proposition, right? So in other words, predicate is essentially expresses some property about some set of things. And the moment you substitute a particular value from that set, you obtain a specific property. Okay. Now, given a predicate phi of X, we can have two statements, two quantified statement. You have this and you have this. As I mentioned in the previous session, this stands for there exists such that phi of X, and this is for all X such that phi of X. So this is an example of existential quantification. And this is an example of universal quantification. Okay. So in first order logic, in addition to atomic propositions and connectives, we have predicates and quantifiers. Predicate is nothing but function of one or more variables that yields a proposition the moment you assign specific values for the variables. And given a predicate, we can have two quantified statements, a universally quantified statement and an existentially quantified statement. Now, the natural question is, when are these quantified statements true? Now, so given the existentially quantified statement there exists such that phi of X, its truth value is given like this. Now notice that I'm not really specifying where this variable X is coming from, right? And the moment we want to compute the truth of this expression, we want that. For example, if I consider a statement like X is P implies Q for P rational P and in natural number Q. So we have a predicate phi, and that phi of X stands for that X can be expressed as the ratio of a rational number and a natural number Q. Now, if I consider the universally quantified statement for X phi of X, now if X is coming from real numbers, then we know that phi of X is not true. Because if you consider X to be pi, then it's famously known that it cannot be expressed as a ratio of two rational numbers. However, if we know that our variable X is coming from set of integers, then phi of X is true for any X. So the point is that in order to determine the truth value of quantified statements, you must know the domain of quantification. That is the set from which the variables in the predicate are coming from. Okay, and this is a point that I made in the last session as well. So anyways, so given this statement, there exists such that phi of x, the truth value of this statement, given the domain of quantification is x, is given like this. So you take the truth value of phi of x as x varies over the entire domain of quantification, and then you take the maximum. And similarly, the truth value of the universally quantified statement for every x such that phi of x is obtained by taking the truth value of t, is obtained by taking the truth value of phi of x as x varies your as x varies over your domain of quantification, and then you take the minimum. Again, I discussed this in detail in the last session as well, so I'm not being very elaborative about this, right? So refer to discussion sessions for more elaboration. Okay, now, so in first order logic, we have predicates and we have the ability to quantify those predicates. We have two types of quantification, existential quantification and universal quantification. And we have seen how do we determine the truth value of such quantified statements. Now, so we saw that using propositional logic, we can model certain complicated expressions, right? So the one that we considered was that a person has a driving license if that person has passed the some test or some other test, something like that, right? Now the thing is, you cannot logically model a lot of sentences in natural languages using just propositional logic. Namely, if you have a sentence like all men are mortal, for example, how do you model this using propositional logic alone? Now you can say that, okay, why this is very simple, right? Why I'm making such a big fuss about this? Simply call this statement this as all men are mortal, right? It can be done using propositional logic. I simply set all men are mortal as proposition P. Now suppose I know an additional piece of fact. I know a Q that Socrates is a man. Now, our brain, the way we think, tells us that all men are mortal and Socrates is a man, should allow us to conclude that Socrates is mortal. But can you arrive at that conclusion using propositional logic itself? So, if you set P to be the proposition all men are mortal and proposition Q to be Socrates is a man, then we have P and Q. Now, common sense tells us that Socrates is mortal. This proposition is true. This much we know. Now, from P and Q, can we arrive at art using the rules of classical logic, using the rules of propositional logic? Can we do that? It turns out no, right? Because in propositional logic, we we start with atomic propositions A1, A2, P or Q, whatever symbol you want to use for them. And we never question the internal structure, the internal content of those atomic propositions. So in that is why they are referred to as atomic propositions or atoms. We don't question what is inside atom, right? We in fact take it as the building block. And on the basis of those atomic propositions, we construct more complicated propositions, right? So therefore, propositional logic by itself is not adequate to capture reasoning like this, that all men are mortal and Socrates is man, therefore Socrates is mortal. You cannot infer that, right? You cannot even capture a statement like this, meaningfully capture a statement like this in propositional logic. You can simply set that statement, all men are mortal, to be a proposition, but that won't get you any far, won't get you so far. Okay. So this is a nuance that you should really appreciate because there's a very natural motivation to jump to go to first order logic from propositional logic, right? And that motivation can be found simply in the way we talk, right? And simply in natural language. right? So long story short, first order logic enable us, and by the way, sometimes people call first order logic as first order predicate logic. So if you want to do that, you can, but I prefer first order logic only. For So first order logic enables us to logically model a very big chunk of natural language statements. Right now, you can talk about all men are mortal. Some students in the class are naughty. Some place in India is extremely clean. Statements like this, right? Whenever, because if you think about it, a large chunk of the sentences we use to communicate in our daily communication has to do with some quantification, right? So just take a moment to recognize that. Okay. So let us consider this set of five statements in natural language in English and try to convert them into their logical counterparts. So the first statement is all men are mortal, right? So we are talking about men and we are talking about being mortal. So let us define two predicates. Men X, standing for X is a man, and let us define another predicate, mortal X. X is mortal. So this translates to for every X, if X is met, then that means X is mortal. Okay, so I want to logically translate this natural language statement. So towards that end, we define two predicates, man and mortal. And then it is clear that this statement can be translated to for all X, if X is man, then X is mortal. And here, the domain of quantification is basically the set of all humans. So I'm not really indicating here that for all X belonging to some set X, right? So domain of quantification is not explicitly stated all the time, right? It's very common to omit the domain of quantification, right? And it's implicitly understood. But I'll just write it here to make things clear. Here, the domain of quantification is the set of all humans. So for every human X, if it happens that X is a man, then X is mortal. Okay? Let us look at this statement. So for every X, every lion is a predator. So for every X, if X happens to be lion, then X is predicator. And what would be the domain of quantification? It could be a set of all animals. Now, let us look at the third sentence. Some student is clever, right? So some, some means at least one, there exists. So here we are talking about existential quantification, right? Because we are talking about some student, not all students. Therefore, this translates to there exists such that student X and the fact that it student is also clever. Now figure out an appropriate domain of quantification for this statement. I will not mention it. So take it as an homework. So every student respects the principal. So we have a particular person, the principal, and it happens that every student is respecting him or her. In other words, there exists P such that P is principal and for every X, if X happens to be student, then X respects the principal. Every student respects the principal, which means there is some principal P such that every student X respects P. Logically translating it gives us this that there exists a principal P, there exists P such that P's principal And for every x, if it happens that x is a student, then x respects the principal P. Okay. So it's a good exercise to just take state a bunch of natural language statements and try to find their logical counterparts. It helps you think clearly and understand first order logic better. Lastly, we have every person loves at least one book. So if you take any person, it turns out that person loves one book. Now notice that here we had the article, the right, and that suggested us that we are talking about some definite principle P which has this property that every student respects him or her. In this case, on the other hand, we have just that every person loves at least one book. So the book that person loves depends on the person itself. So I may love Harry Potter, you may love Lord of the Rings, and so on, right? So you have to identify that here the book under consideration depends on the person we are talking about. In other words, I would translate it like this. For every x, if it so happens that x is person, then there exists y such that y is a book and x loved the book y. So take some time to convince yourself that these are the appropriate logical translations of these statements. Okay, so that um, completes the section on first order logic, right? Now we will move to multi-valued logic, which is in a sense what this course is about. It's about fuzzy logic, and fuzzy logic is an example of multi-valued logic, right? So we have seen that a lot of statements can be logically modeled using propositional logic and first order logic. But it was eventually realized that these logics, the system of logics, are based on two truth values, 0 and 1. And two truth values are not sufficient to describe the richness that we have in real world. So for example, suppose I consider a statement like this. So I have a statement, say P, and that statement says that this statement is false. Okay. I have a statement P, and that statement P is this statement is false. Now, how do I assign a truth value to P? Suppose I say that truth value of P is 1, that is P is true. Then the internal content of P suggests us that P is false. Similarly, if we assign P to have truth value 0, that is, if we assume that P is false, then the very nature of P suggests that P is true. So we arrive at a paradox, a contradiction, right? And in fact, this is famously referred to as Bayes' paradox. And logicians and mathematicians grappled with statements of this sort. And they quickly realized that having two truth values aren't enough, right? We have to have more truth values. So one way to resolve this Bayes' paradox is to introduce a new truth value. And suppose I denote that new truth value as half, and half is understood as indeterminate, suggesting that if we assign a particular statement the truth value of half, then we are not able to meaningfully give a truth value of 1 or 0. So in this case, truth value of P can be assigned as half. Okay. So the point is that our world is complicated and very rich, and two truth values aren't enough to describe this richness. So there is a natural motivation to go from classical logic, which are based on two truth values, to multi-valued logics, which are based on more than two truth values. Okay. Now, I should mention that in the start, I talked about different logical traditions. So I talked about Aristotelian logic, and I also talked about a few Indian schools of logic. So Chaturskote is one Indian school of logic. And interestingly, it is based on the idea of four truth values. You also have a Jain school of logic called Syalvat or Saptalangi, which are based on 7 truth values. So the point is that this realization that we need more than 2 truth values to adequately understand the world around us. This has been around in the Eastern world, in India and China for quite some time, right? But a proper mathematical formulation of a multi-valued logic came from this person named Jan Lukasiewicz. He was a Polish logician, and in 1922, he proposed what can be considered as the first proper mathematical proposal of a multi-valued logic. So he gave a 3-valued logic. So this is basically Jan Lukasiewicz. He was part of this Polish school of logic, which is really famous. They did a lot of very important contributions in math and logic. So, anyways, so Lukasiewicz proposed a system of logic in which there were 3 truth values: 0, half, and 1. And we again have 4 connectives. We have negation, not, we have and, we have or, and we have implication. And the truth value of the propositions constructed using these connectives are given as follows. So let us first focus on the truth value of negation of P. Again, you could have used the symbol tilde P as well, but um, you can use them interchangeably. So if P is false, that is when P is 0, truth value of P is 0, then truth value of not P is 1. And when truth value of P is 1, then truth value of not P is 0. So when we have the standard true false truth values, then negation behaves in the normal way. And when we have indeterminate truth value half, then its negation is also going to be indeterminate truth value. It's going to have indeterminate truth value. So this is how the connective not behaves in the 3-valued logic of Lukasiewicz. And the truth value of P and Q is obtained by taking the minimum of truth value of P and Q. Similarly, truth value of P or Q is obtained by taking the maximum of truth value of P and Q. And truth value of P and Q. Now, notice that these 2 definitions coincides with the definition of truth value of and or in classical logic as well, right? So, in a sense, any multi-valued logic is supposed to generalize classical logic. So therefore, when our truth values, if we just consider the connectives on truth values 0 and 1, then they should behave similar to classical and classical or and classical implication, classical not, right? So that is something that we must keep in mind, that multi-valued logics are supposed to generalize the classical logic. Anyways, and this Lukasiewicz defined implication in his 3-valued logic by this formula. The truth value of P imply Q is minimum of 1 minus truth value of P plus truth values Q. And this is basically why we call this implication Lukasiewicz implication. Now the question is it the only way to define an implication in a 3-valued logic like this? The answer is no. Maybe we can come up with something else. But the point is that Lukasiewicz defined the implication in this manner, right? And this is, in a sense, the birth of modern multi-valued logics. This implication is essentially the birth point of modern multi-valued logic. So you should take a moment to recognize that this is very important. This is seminal in a sense. Okay. Now the truth value half, as I just mentioned, stood for indeterminate or possible, right? So another interpretation is that we are not able to ascribe a definite truth value to the statement, this particular statement. Then we can call it half, and half can be interpreted as indeterminate or possible. Okay. Possible essentially being used here as a synonym for indeterminate. If it is too confusing for you, maybe I should remove this. So simply uh, think of half as indeterminate. Now, Ukashevich soon realized that we can have more than three truth values. And having more than three truth values enable us to model sentences in natural language much more finely, right? And he proposed an n-valued logic for positive integer greater than equal to 3. So he gave so 1920 his 1920 paper was about L3, a three-valued logic, and soon he realized that we can have more than three truth values, and that would better help us model the um, statements in a much better manner. And then he gave the general n-valued logic ln for some positive integer n greater than equal to 3. Now in ln we have n truth values, namely 0, 1, 2, 1 by n minus 1, 2 by n minus 1, all the way to n minus 1 by n minus 1, or basically 1. So we have 0, 1 by n minus 1, 2 by n minus 1, all the way to. So ln has n truth values, and we have four connectives, not, and, or, and imply, and they behave in this manner. The truth value of not p is 1 minus truth value of p, and truth value of p and q are defined like this in terms of minimum and maximum of truth values of p and q. And this implication is used to determine this formula is used to determine the truth value of p imply q. Okay. And remember, right, which is this particular set. Now it can be easily seen that in fact you can take this as an homework. So truth of p and truth of q are numbers in this set, right? 0, 1 minus n, 1 by n minus 1, comma 2 by n minus 1, all the way to 1. So this formulas 1 minus TP, minimum of TP and TQ, maximum of TP and TQ, minimum of 1 minus TP plus TQ. These are also going to be some numbers in in this set only. In other words, these connectives are well defined, right? So it's useful to sort of recognize that these are actually well defined. So, anyways, Ukashevich in 1920 gave a three-valued logic in which we had, in addition to the usual 0 and 1, 1 by 2. Soon he extended his three-valued logic to an n-valued logic, ln, where n is some positive integer greater than equal to 3. The truth values in ln is this set, and the four connectives behave in this manner. Okay. And soon, Ukashevich collaborated with another logician named Tarski. So Tarski is like a superhero when it comes to logic. And Ukashevich collaborated with Tarski to propose an infinite valued logic, which is denoted as L infinity. And in L infinity, instead of having finitely many graded truth values, 0, 1 by n minus 1, 2 by n minus 1, and so on, the truth values vary continuously in the unit interval. So your entire unit interval is the set of truth values. And the four connectives are defined in the usual way. Okay. So this is, in a sense, the birth of fuzzy logic. The term fuzzy logic came much later, but this idea of using the entire unit interval as the set for truth values came up with this work of Lukashevich and Tarski, right? And it's a type of fuzzy logic. Why I'm saying it's a type of fuzzy logic? Because in fuzzy logic, you can use another connectives as well. You don't need to use minimum for and maximum for or and this particular implication. You can use any kind of you have a much larger set of choices, right? So in that sense, this infinite valued logic of Lukashevich and Tarski is a type of fuzzy logic. Okay, so I hope I hope you realized why multi-valued logics, first of all, are important to consider, and this historical development of Lukashevich logic and the logic of Tarski. Now, I will quickly solve a couple of problems based on Lukashevich logic, and then we'll conclude the session. So the question tells us that we have four valued logic of Lukashevich. So remember, in four valued logic of Lukashevich, we'll have these four truth values. And we have two statements. The device is charged and the light is on. And we know that the truth of first statement is 2 by 3. And the truth value of second statement is 1 by 3. And we are required to determine the truth value of the following statement. The light is on provided the device is charged. So we first need to convert this natural language statement into a logic. We need to figure out its logical translation. So this is S1 and this is S2. Light is on provided that the device is charged. What is the logical translation of the statement? It means that if the device is charged, then light is on. In other words, logical translation of this is S1 implies S2. That if device is charged, then the light will be on. So S1 implies S2. And we need to compute the truth value of S1 implies S2. Now we know how the truth value of S1 implies S2 is computed in Lukashevich logic. It's basically using this formula, minimum of 1 comma 1 minus truth value of P plus truth value of Q. So we simply right? So 1 minus 2 by 3 is 1 by 3. 1 by 3 plus 1 by 3 is 2 by 3. And minimum of 1 and 2 by 3 is 2 by 3. So the second option is correct. Okay. So let us move to the next question. We have a 7 valued logic in this case. So remember L7 is going to look like this. And we have three statements, S1, S2, S3. They stands for the report is complete, the data is accurate, the deadline is met, respectively. And the truth value of these statements. So T of S1 is 5 by 6, T of S2 is 1 by 3. 1 by 3 essentially is 2 by 6, right? And then we have truth value of third statement, which is 1 by 6. And I need to determine the truth value of this statement. The data is accurate or the deadline is met if the report is complete. Now remember, Q if P, this is something we discussed, right? This essentially means P implies Q. This is just another way of stating P implies Q. Q if P. I hope you remember that. I hope everyone is like remember this. So the data is accurate. This is basically S2 or the deadline is met. This is S3. So this whole thing, and we have an odd here. So this is S2 or S3. The report is complete. So this corresponds to statement S1. And we have an if here. So if we logically translate the logical translation of this thing is S1 implies S2 or S3? Just take a moment to recognize this. We have this statement. We identified the parts of the statements that are S1, S2, and S3. And then we notice that we have an if here. So when we logically translate this statement, we'll have if the report is complete, then the data is accurate or the deadline is met. That is S1 implies S2 or S3. And I need to compute the truth value of this expression. So this is minimum of 1 minus minimum of 1 comma 1 minus truth value of S1, the left part of the implication, plus truth value of S2 or S3. But what is the truth value of S2 or S3? This is maximum of truth value of S2 and S3, which is maximum of, now truth value of S3 is 2 by 6 and truth value of S3 is 1 by 6. So maximum of these two numbers 2 by 6. So this becomes minimum of 1, 1 minus truth value of S1 is 5 by 6. 5 by 6 plus 2 by 6. In other words, it's minimum of 1 comma half. So 1 minus 5 by 6 is 1 by 6. 1 by 6 plus 2 by 6 is 3 by 6, which is nothing but half. And minimum of 1 comma half is nothing but half. So the truth value of this statement, the data is accurate or the deadline is met if the report is complete in the 7-valued logic of Ukashevich is half. So I hope you all understood this example. So this was the last example I had for this discussion session. So thank you. Any questions?
No questions, sir.
Okay. So in that case, I'll conclude. Uh, Stop the recording.